So how many like there's a helium nucleus. So what is the mass of nucleus? MF, I'll write it. So this will be 4.00260 atomic mass unit U. Then it is made up of what? Two protons, two neutrons. So what is the mass of? We are discussing the binding energy, no? Let it be here. Now, protons, neutrons, they're separated to infinity actually. They come and form the nucleus. Initial mass of system is equal to how much? 2 times of mass of neutron, 2 times of mass of proton. This is the initial. This is the final. And we'll get binding energy released. So what is the initial mass of system? It will be 2 into 1.00. I have data. I'm mass of proton 0.7825 U. Okay, this is about the initial mass. I think somebody should give me the value. Initial mass. Anybody value initial mass?
4.0330, sir.
4.0330 U.
So I considered only 2 decimal places, sir.
No. You have to take 4 decimal or 5 decimal. Please don't do any approximation. Very dangerous. 4.03298. 4.03298. Okay, thank you, Meghana and Gayatri. Okay, this is initial mass. This is the mass of helium nucleus. Okay, now, okay, these are the two protons, two neutrons are there. I know their mass. Like two protons, two neutrons, they come together, they form a nucleus. Then what do we expect? This, sir, what is their sum of this? This should be the mass of nucleus. No, the mass of nucleus is this much. Sir, how come? Initial mass is something this one. The mass is here less. Are you seeing now? 4.0026, 4.03298. MF less than MI. Where do that mass gone? Convert into binding energy. And that binding energy is utilized to bind the nucleons together. Where do that energy will come? The energy will come due to mass defect. This is the core central idea of the entire nuclear physics. Shall I put simple? You take 4 marbles. You know mass of each marble, let it be around 10 gram. Then you stick them. Then you measure the mass. How much it will be? The same, 40 gram only. But here the nucleus will not happen. At subatomic range, it will not happen. When you go and check the mass of nucleus, it will be less than the sum of its constituents. Means 10 kg tomatoes you are going to purchase. So in 10 kg there are 20 tomatoes will come. You measure the mass of each tomato. Okay, fine. Then when you put in basket and you measure, it will become less. Sir, what is this? Where do the remaining mass gone? Convert into mass defect. But at gross level it will not happen. At subatomic level it will happen. Means, sir, with the tomato it will happen or not? You clarify. No, it will not happen. You check it. You measure the mass of each tomato. Okay, fine. Then put in basket. Then you measure it. Mass of the basket you can let it be negligible. Now we have polythene covers, everything. When you measure the some 10 tomatoes, no, it will be equal to the sum of individual mass of tomatoes. But at subatomic level it will not happen. Okay, are you getting now? Mass of this one. Where do that remaining mass gone, sir? Convert into energy, and that energy is utilized to bind the nucleons. This is the core central idea. Mass defect. which is equal to mi into mf, mi minus mf. So this has to be calculated. All our nuclear reaction just revolves around this idea only. Nothing is there. Only you have to very good in addition subtraction. 4.00260 U. Yeah, you have to give me value. No approximations up to 4 decimal or 5 decimal places. You have to carry on your mathematics. Anybody delta M? 0.02988. 0.3038. Oh, this will be EU. Convert one AMU. One AMU, you can convert this. Now binding energy will calculate. What is the binding energy? Binding energy equal to delta M into C square. What is delta M?
Sir, it will be 0.02988, sir.
2988.
Yes, sir.
931. Anybody? Just final value, binding energy. Vinayak Nitesh, energy mass is conserved here. Modern physics, when you enter, we'll never go for energy nor mass. We always say that energy mass is conserved.
Yes.
Anybody value? I think I'll go for calculator in my mobile better. Multiply these two, 0.02988. 27.81828. 27. This much of energy is available for us. 81828. Now where do this energy will be utilized? Will be utilized to bind the nucleons together by a nucleus. Sir, how do nucleus will come to know to do all this operation? We don't know. that please don't ask me. Sir, why it happens? Sir? Gayatri, Gunetra and Srija. You 0.0308 and 0.0298. Okay, anyway, some nearest. Okay, there's a binding energy. So what makes the nucleus to behave like this? At gross level, why we don't see? Only at subatomic particles we see like that, and we are made up of that. Okay, these are questions we are unable to answer, but practically I say you purchase 10 tomatoes or 10 tennis ball, you take it, measure mass of each ball, then combine them, because they don't get interact. No, there's no interaction. So when do such a mass defect will come? When there's interaction will come. Two tennis balls or pen, they don't interact. No, of course gravitational force will come, there's a thing, but they don't interact here. But the nucleons, what happen? They interact. This is what happens here. So what makes them to What makes this to form a nucleus and why they do behave like that, we don't know. That is all beyond our science what we know it. Like this, we'll calculate this binding energy. Now this binding energy is what I'm going to use to define the stability of a nucleus. So with the help of this, what will happen? I can go for the binding energy per nucleon concept. So how we define is the binding energy per nucleon. We take help of that. With the help of that, what will happen? We'll define the stability of a nucleus. So now what we do is like this binding energy. Okay, we'll discuss some binding energy, some related to collisions. Then I'll start the stability afterwards. Okay, just make observation. Like this, you calculate in various books they're given. You should know how to calculate binding energy per nucleon of the different materials. Let's explore some numericals on this binding energy.
Sir,
Yeah.
sir, it is 4.03 to 98, no, sir.
Z 03298, no? Yeah.
So it will be different, sir.
What is the value?
Sir, 3038 only, sir.
3038 only, yeah. Oh, I have to make all changes. How much? 30?
03038.
Here also will change then. Okay, yeah. Then final. 27.81828. Yeah, some more. Okay, now we'll
28.28378, sir.
Yes, sir.
28 point.
28378.
Okay, no. This is about the binding energy. So can we calculate binding energy per nucleon? How many nucleons are there in nucleus? 4 is used to define the stability of nucleus. So what is the binding energy per nucleon? Very important parameter. So this will be 28.28378. This anybody divided by 4? Hurry up, we'll discuss some problems on binding energy. .0709. This will be the binding energy per nucleon. Like this, we will calculate binding energy per nucleon of various nucleus that are present here. I think around more than 2000 nuclei are there. We'll calculate all the binding energy per nucleon. With the help of this data, we can define the stability of a given nucleus, why they are stable or unstable. That stability we'll discuss in the later part. We'll just explore how the physics involved with this binding energy. This is something very important for us.
Sir, how did you say 2000?